Hi everyone, this is a very spontaneous video which I would like to share with you how the space-time antenna actually functions with the load, and it's producing DC current. It's not actually the setup which is supposed to be. We need to make this device here actually functioning and converting the higher frequency in DC. But what I'm using here, it's a very small capacitor, 6.3 volts, this one here, which is 3300 microfarads, and there are two diodes. Perhaps it's difficult to see, but there are two diodes in order to rectify the current, the AC current, and we have also ground. I will do other video to explain better this setup, exactly what is here, but this is very spontaneous video which I would like to share several things. Now this is the red lead. It's from the top, which is connected with the Merkaba, one end of the Merkaba, and the black one is from the other end of the Merkaba. Merkaba, it's in the core, has a central rods they are connected and protrude through three iterations of spheres, and there is an insulation. So we are supplying the signal to the outer shell of the sphere. We connect only the positive end. It's a bit difficult to see because it's dark, and the negative we leave it like a virtual ground, in a sense, in order to pose like a monopole or like a dipole this huge sphere. Now at that moment I'm supplying 7.2 million cycles per second with 12 volts from peak to peak. You can see here 12 volts peak to peak, 7,200,000 cycles per second. And you can see there are two LED lights which are each 6 volts, and the capacitor, I told you, it's 6.3 volts, 3300 microfarads. There are two diodes of each end, and one of the diode is connected to the positive and the other one of the negative of the space-time antenna. In this case, it doesn't matter which is positive and negative because the current is alternating. The reason I'm shooting this video is because I would like to share with you how this brightness, it will change when I'm changing here the frequency. Maybe I can go a little bit back, and I will start to roll this knob here, and I will reduce the frequency. Right now it's 5 megahertz. Right now it's 3 megahertz, and you will see that the brightness, it's going down. Now we are 2 megahertz. There is almost no light. Now it's 1 megahertz, and now it's 100,000 cycles per second. So you see that there is nothing. Let me go up. Now it's 2 megahertz. I will make close up to see. It's 2 million cycles. There is nothing. But when we approach the resonant frequency, it's going brighter. In the previous video I told you that the resonant frequency is 4.4, but because we're using a capacitor now which has certain reactance, it probably changed the frequency and make it higher, the resonant frequency. Now it's 3 megahertz, and you can see that the lights start to be brighter at 3 megahertz. I will tell you, now it's going to 4 megahertz. You see, going back at 3. At 3 it's a little bit brighter. At 4 it's not so bright. But as I go more than 4, now I'm going to go to 5. This is 5, and this one is 6. You can see that at 6 it's much brighter. Let me show you. It's a 6 megahertz. And now when I'm going to 7, it's even brighter. You can see this is a very simple video which I would like to share with you. A few things. First, that the brightness is changing with the frequency. Now it's 8 megahertz. Now let's go to 9. Let's increase the frequency. 9, you can see that they go back not so bright, like more dim in a sense. This is 10 megahertz. At 10 megahertz, let me clean the video a little bit. At 10 megahertz, they are not so bright, the light bulbs. I will go back to 7.2, and you can see that they're much brighter. So the first thing of this experiment is that when we change the frequency at a specific frequency, the LED lights, which are working with DC current, they receive much more energy at the resonant frequency, which in this case is 7.2 megahertz. But there is something else I would like to share. This setup, it's working very similar to one of the to Nikola Tesla prototypes, because we are using ground here. You can see this is the ground, okay? The wire, it's coming from the ground, and it's connected to one of the capacitor leg. Doesn't matter which one. I will detach it. You will see that they are still they still have power, they're still working, they're still bright. But when now I'm going to connect it to the positive, let me 1 second. Now you can see they are much brighter. I will detach them now, and you can see the brightness diminish. I'll connect it to the negative now. 1 second. Here it is. Again, much brighter is the lights. And when I connect it to the positive, also much brighter. So it doesn't matter which end, but if I ground it, one of the legs of the capacitor, the lights are much brighter at the resonant frequency. I'm going to use it now, the oscilloscope. My oscilloscope is here. I have a probe, and the probe, this one is the ground. So it's not working, the oscilloscope. I will check if I ground it with a probe from the oscilloscope. And you can see, now as I touch the ground of the oscilloscope, I attach the ground, and the light bulbs are much brighter. So it doesn't matter if it's directly from here, because maybe some of you may think that you know, make some tricks, I don't know, but this is the prop of the oscilloscope. It's connected over here. Really bad quality video, I'm sorry, but this is very spontaneous. So when I connect the ground, which is this one actually, and you can see that the lights are actually getting much brighter. When I detach it, they're not so bright. So the first thing in this video is that those DC LED lights are much brighter at the resonant frequency, in this case 7.2 megahertz, and also we need to have a ground in order for them to have full power. And it's not working, this setup, with any capacitor. I check other setups, but it's not working with any other capacitor and any other diodes. I have a lot more things to research here and to see what actually is going on. But here it is. This is a signal, RF signal, which we are sending to this sphere at very high frequency, 7.2 megahertz, and we are having DC output to the lights, which are flashing at the best when we approach this frequency. Now this is just a video which I'm going to shoot it again, and I will make maybe schematics for you to see what actually we are doing. But for now, I was very excited, and I just wanted to share it with you what actually is going on here as an output when we connect also a load.